This is Doing Every Challenge question, part 48. This is Core Pure 2 Review Chapter 1. This is going to have the hardest questions that we've done so far. In particular, this question, which I thought was horrendous. But it was also quite fun. There's just a lot going on here. You have to be very good at all of Chapter 1, I think, and perhaps some other things as well to get this done. Anyway, omega is this complex number here, so that's fine. Show this thing if this or otherwise. So, okay, w to the, or omega or w, I'm just going to say w, I think, to the n is just this with an n in the thing. And w squared is just this with a 2 here and then with an n next to it. So that's fine. Okay, so we got that. All we really have to do, so this is the thing we're looking at now. All we really have to do is just test what happens if n is 0. So I'll put n as 0 in first. That just makes e to the 0 plus e to the 0, which is 1 plus 1. So 1 plus 1 plus 1 over 3 is 1. So that checks out. And then we just have to check what happens when you put in a multiple of 3. So we can just pretend n is 3k, for instance. It's never actually said that n is an integer here, but I think it has to be, right? I think that's implied. Anyway, so n is 3k. We'll just go test for the multiple of 3. So let's put 3k in here, which makes a 6k here and a 12k here. But 6 over 3 is 2 and 12 over 3 is 4. E to the 2 pi, where k is an integer, or 2k pi, is just 1 because you've gone all the way around to 2 pi an integer number of times. So you've just arrived at 1 again on the Argand diagram. And likewise with 4 pi. So this is just 1 plus 1 plus 1 over 3, which is 1. So we've checked this bit. Now we need to do otherwise. So now we need to set n is equal to 3k plus 1. You get this if you do that. I put in 3k plus 1 here and then expand it out. And now I can break this fraction. I did the same thing over here. I can break this fraction here and here. And 6 over 3 is just 2k pi and 4k pi over here, as we had before, which we know are just 1 and 1. And that just leaves 2/3 k pi and 4/3 k pi over here. So that leaves this here. And this is where we have to reach for something that we saw earlier in the chapter. Notice how omega is a root of unity. It's 2/3 pi I. That means if you cubed it, you just get e to the 2 pi I, which is 1. And so therefore, omega is a root of unity. There's a really nice little fact about those things in the book here, which is, so we've only got 3 of them, right? Because this is the cube, or the cube root of unity, or omega cubed is 1, which means 1 plus omega squared is 0, which is what we've got here, and therefore 0 over 3 is 0. So I'm using this fact here because n minus 1 is 2. We stop at 2, and we get this as 0, and we're done here with that. And n equals k plus 3k plus 2 goes basically exactly the same, right? You get this. Now 8 over 3 is 2 and 2/3, but 2 is just a whole turn around the Argand diagram, so it doesn't matter. So you're just left with 2/3, and this is just 1 plus omega squared. So okay, therefore, and where omega is again a root of unity, so again that's 0, and we end up with this here. So that's the first part done, which is actually the easiest part of this question. Next, it goes off on a spiel about f of x is a polynomial, largest power multiple of 3. So okay, just some polynomial written here. The sum s is given by, so the sum s is the sum of the coefficients of the multiples of 3 powers of x. So the first one, and then the one that's next to x to the 3, and then next to the 6, and so on. And they're giving me that there. By considering f of x, show s is f evaluated at 1 plus f evaluated at omega plus this. Now, clearly, we're going to have to use this fact here at some point. But how do we do that? So, okay, firstly, f of 1 is just this. F of 1 is just all of the terms when you evaluate it at 1, which is just all of the coefficients added together. F of omega is all of the things with an omega in where x is. And f of omega squared is where you put omega squared in instead. And therefore, the first term is omega squared, and the second one is omega squared squared, which is omega to the 4. Next one would be omega squared to the 3, which is omega to the 6, and so on. Now what I'm going to do is I'm going to add up all these 3 things and divide by 3 at the same time. And I'm going to add up in like a column form. So the first ones are just a0 plus a0 plus a0, which is a0, which is 3a0. And then when I divide that by 3, I'm just going to end up with a0. Next ones are going to be a1 plus a1 omega plus a1 omega squared, which is a1 into 1 plus omega squared over 3. And likewise for the next one, where it's 1 plus omega squared plus omega to the 4, and the next one, and so on. Now, what's interesting about this is we've already decided that this thing here is 0, and because of the roots of unity adding to the right thing. And now, based on this idea here, I think this can be written as 1 plus omega to the 2 plus omega to the 2 to the 2. So it's this whole thing is therefore this thing when n is 2. But if n is 2, it's 0. So, and the same thing, you can argue the same thing here where n is 1, and it's therefore 0. So this is 0, this is 0. This is 1, because this can be written as 1 plus omega to the 3 plus omega to the 2 to the 3. And when n is a multiple of 3, that whole thing equals 1. So this is 1, which makes this, sorry, this whole thing, yeah, this whole thing with the divide by 3 is 1, which means I just add in a to the 3. And the whole thing will continue with that, and you'll just be left with one lot of each of the multiples of 3 things, which is what S was defined to be. And so therefore, we've shown that this is the case. I think that's done. Okay, good. Hence, by considering, hence by considering the binomial expansion of this, show this thing here. So, okay. So let's call f of x. Now, this thing here, the only thing I can relate this to is f of x, because this is just a polynomial, right? Like it's a polynomial with a bunch of really big coefficients all the way to x to the power 45. So let's call f of x this thing here, which is, and you can write that in like its binomial sum form of this, where you're using the choose functions to define it, so that's fine. So okay, that's f of x. And now, okay, this thing here is the sum of just the multiples of 3 coefficients, isn't it? Because we're just using 15 of them, and we're skipping every time, because this 3 here skips a bunch of coefficients. So this is just interested in the multiple of 3 coefficients, which is what we defined to be s earlier, as it relates to f of x. But then we said that s is equal to this thing here. So this thing here is s as it relates to f of x, which is this. And s we know from part b is equal to this when I evaluate f at 1, omega, and omega squared, add them together, and divide by 3. So this thing here is just s. Does there need to be an x 3r's here? I'm going to hope that I deal with that later. Okay, that thing there is just s, which equals this thing here, based on this definition here. I've just written this third in the front here like this. Yeah, no, I don't need this here. I'm being an idiot. S, of course, doesn't have any x's in it from the original thing, so this is just a mistype. This shouldn't exist here. That just needs to go away. Okay, that's fine. Anyway, so s is just this thing here. Now, f of 1 is just 1 plus 1 to the power 45, so that's just 2 to the power 45. F of omega is 1 plus omega to the 45, and then f of omega squared is 1 plus omega squared to the 45. So, okay, that's cool. This thing here, this thing shouldn't exist, is equal to this. How do I get that to look like this? Well, with some very clever trickery. Again, going back to that thing we talked about earlier, because omega is a root of unity, 1 plus omega squared was 0, based on that thing that the textbook told us earlier. Which means, if I rearrange this, 1 plus omega is minus omega squared. And likewise, 1 plus omega squared is minus omega. So that looks like it's a bit simpler. Now, this is the power 45, so there's 45 negatives here. So I could just put the negative out the front and ignore it, and likewise here. So I think I can just write it like this. And now 2 to the 45. What is 2 to the 45 if not 2 to the 45 plus 1 minus 1? That seems legit. And now I think I can write this thing. If I factorize out the minus 1, I can write it like this. But this here is just of the form this thing here, right? Where n is 45. 45 is a multiple of 3, which makes this whole thing, because it doesn't have a 3 underneath it, that makes this whole thing 1. Makes the whole thing 3, right? Because then 3 over 3 is 1. So this whole thing, because n is a multiple of 3 in this case, this whole thing is 3. So I think I can write just replace that thing with a 3 to make it there. That makes a minus 2, and I think I've arrived at what they wanted me to get. That was the hardest thing we've done so far in the challenge questions, but it was also really fun. So cool. This then immediately is one of the easiest things we've done in the entire challenge question series. We're literally just doing a volume of revolution around the x-axis, which of course is the integral of y squared. I can call this thing y, I guess. Integral of y squared dx, or pi y squared dx, I guess. But y squared is just you just get rid of the square root. So you're just integrating this thing here, which is super nice and easy because we can just break this fraction in half here, simplify these up, and literally just do a year 12 integral. It's really nice. So I'm just going to do the integral. When you put in infinity, this is 1 over x, and this is 1 over x squared. So of course 1 over infinity is basically 0, so this entire first term goes away. So it's going to be 0 minus what happens when you evaluate it at 2. This is a half, this is a quarter to make 3/8. So you make this. This is 4/8, I guess, and then this is minus 7/8, minus makes plus, and you make 7/8 pi. Really, really easy question, done. Question 3, they have ambushed me with some stats, which I do not appreciate, but it's fine because it's actually good stats. It's about integration, so it's good. A is constant, so okay, integral of f of x between infinity and minus infinity. So just bring the a out, I guess. Because it's a constant, I don't need it. This integral is in the formula book. It's of the form this, where a is 1. So that just makes 1 arctan of x, which is easy. Arctan of infinite, you're supposed to sort of say, okay, so for what value, if you inverse the tan, it's tan of what value equals infinity? Well, that's going to be pi over 2, I guess. And minus infinity, likewise, the principal solution is minus pi over 2. Minus minus make a plus, you get pi, therefore a pi is 1, a is 1 over pi as required. The variance is defined by this thing, where you times f of x, which we know to be 1 over pi times this, by x squared. So okay, I'll just bring the 1 over pi out because it's just a constant, and I'll do this integral. This integral took me a hot second to work out how to do, but actually you can just say that this is x squared minus 1 plus 1, and then break the fraction here to say this is 1, because that over that is 1, minus 1 over this. And now this is just the arctan integral we saw before. This integrates to x, so that's fine. When you put in infinity here, you're going to get this. And because this is a plus infinity, you just end up with 2 lots of it, and therefore it just has infinite variance. Like, this just doesn't end up being a nice number. So cool, that's pretty much that. So that's done. And the last part, show this thing. So this time we're only timesing the function by x. So okay, that's fine. And by the way, the mean is given by x, f of x, which is why they're doing this. Although it didn't actually explain that, did it? Oh no, it did. Sorry, the mean is defined by x, f of x. Okay, sure. Okay, so let's work out this then. So this is just a log because this is of the form f dashed over f. So if I just shove a half in, because 2x differentiates, sorry, x squared differentiates 2x, just put half here and it's fine. We get this here. When you put in the a and the minus a, these two terms are the same, so this just equals 0. So the first one definitely just goes to 0. The second one's kind of interesting. Do the same integral, you get this. When you put in 2a, you get 4a squared here. And when you put in minus a, you just get a squared, obviously. Now, this isn't the same. So let's combine the logs here to make this. And now I'm going to do the same thing I did again, which is write the top of this as 1 plus a squared plus 3a squared. Break the fraction here, and then the first 2 bits just become 1. And this becomes 3a squared over 1 plus a squared. But now this is kind of interesting, I guess, because what you can do here is when you have a limit of a log, you can swap the limit and the log over to make this kind of thing. I haven't proved that here because I can't be bothered, but you're totally allowed to do that. And so now, well, as a goes to infinity, this just goes to 3, I believe, and 1 plus 3 is 4. So this is just a half log of 4, which isn't 0. So therefore, this doesn't equal this. The mean is therefore undefined because the mean, like both of these things, as a goes to infinity, this is the integral between infinity and minus infinity, and so is this, which should be the mean. But it's not, because the mean has 2 different values here. So therefore the mean is undefined because it goes to do different things. That's the video done. Thanks for watching. I'll see you next time.